So in this video, we're going to look at two examples of how to do logarithmic differentiation. The first example is relatively simple, but it is a situation where you have to use logarithmic differentiation. There is no other alternative. We have no basic rules for functions of x to the x. And so logarithmic differentiation is the way that we approach those kinds of problems. The log properties allow us to do some simplification so that we can use other strategies we already know. And the second example we're going to look at is going to be a problem that you could conceivably do without logarithmic differentiation, but it's very complex. Lots of embedded rules, chain rules, product rules, quotient rule combinations, and using logarithmic differentiation will allow us to simplify those problems. All right, so let's look at the first example. So in this case, we have cosine x, which is raised to a function, a power of x, in this case, x cubed. So x to the x type functions are what logarithmic differentiation is generally used for. When the function looks simple, but there's x in the base and x to the power, this is what we have to use. So the strategy basically goes like this. So replace the function with y. So cosine x to the x cubed. And then we're going to take the derivative implicitly, but the trick that we're going to do before we do that is we're going to take the log of both sides of our problem. So we're going to find log y is equal to log of cosine x to the x cubed. Now, the thing to keep in mind, when we have logs, we can use log properties. And so before I go any further, I'm going to simplify this. The main thing that I want to do for a problem like this, where I have x to the x, is I need to bring that power, that x that's in the power, I need to bring that out front of the log. So this will become x cubed log of cosine x. Okay, so now we have this simplified, and so now what we do is we apply essentially our implicit differentiation rules. When we take the derivative of the side with the log y, we have to use the chain rule because it's implicit. Y is a function of x. We're just not writing it down here. So this will be 1 over y prime. And then we take the derivative of our now simplified expression on the other side of the equation. So this is going to still require a product rule. And then again, this is completely typical for these kinds of problems. We have 3x squared log of cosine x plus x cubed times 1 over cosine x times negative sine x. And we can't really do a lot of simplifying in this case. We could write this x cubed, negative x cubed sine x all over cosine x. We could transform sine x over cosine x into cotangent x. But the main thing that we have to worry about is that we want to solve for y prime. And so we're going to multiply both sides of the equation by y. And then this term doesn't simplify at all. But then this next term, what I'm going to do is I'm going to translate this into x cubed cotangent x. And then our derivative, our function was originally in terms of x, and so our derivative needs to be entirely in terms of x. We can't leave the derivative in this present form. And so we're going to replace y with the original function, which was this guy. And then we multiply by the expression that we got in parentheses. And so now this is our derivative of our complex function that we started with, this x to the x function. We end up with the original y and then times the derivative portion that we got from our log simplification and then differentiating that. Now let's look at the other kind of example that we can do with logarithmic differentiation, example 2. And typically this kind of situation, again, is not required that we do logarithmic differentiation for this kind of problem. In principle, this is some kind of a chain rule because we have an expression raised to a power. But then when we go to do the chain rule on the inside, we then have a combination of product rule, quotient rule with maybe more embedded chain rules. And so sure, I mean, that we could do this sort of traditional way. And it would require lots of steps, lots of combinations of rules. And what logarithmic differentiation allows us to do is to simplify before we have to take derivatives. Our expression will look different in the end if we were to just brute force this, but it will be algebraically equivalent to our final answer, and it will require a little bit less work. So let's actually look at this and see how this would work. So again, the idea here is we're first going to follow the same steps. We're going to take y equals whatever this crazy function is. And then we're going to take the log of both sides. So same second step, log y is equal to log of this crazy thing. Yeah. That's why it's not working. Try one more time. Nope. There we go. Sometimes the equation editor has a mind of its own. All right, so, and the same strategy applies before, as we did before. So what we said was when we had an x to the x power, we needed to use properties of logs to simplify. In that scenario, we have no choice because we couldn't proceed. The x to the x power was the thing that was giving us problems. Here, we do it more just to save our sanity, but still, what we should do is we should apply log properties. So this 1/3 cube root is going to come out as a 1/3 power. So 1/3 log of the expression under the root. And then what's different in this case is instead of just applying one, in this case, one power rule, you keep going. So we're going to have our 1/3, and then we're going to apply another log rule. In this case, we're going to apply the division rule. When you have division inside of a log, you turn that into subtraction. So we get log of the numerator minus log of the denominator and then we have to keep going. In our initial expression, we still have a product inside the log. So we're going to apply the sum rule. Log of e to the x squared plus 1 plus log of tan to the 5th x, and then minus what was in our denominator. And then we can apply our exponent rule one more time, which is going to give us, and we'll combine these constants in a second. This one, log of e to some power, that's actually going to simplify entirely. Log and e will cancel. This will just get us x squared plus 1. And then this one, the 5 will come out. And then all that will be left is tan x. And then minus the 7 will come out, and we'll just have log of x to the 4th minus 6x plus 9. And then we can simplify this just one more time, which is just to put the 1/3 through everything. 1/3 x squared plus 1/3 plus 5/3, or not. I mean, it's up to you. It's a constant, so it's not really going to change anything if you don't, but it will make it a little easier later on, I think. Constants won't really change much. Okay, and so this expression, remember, this is log y is equal to this. Now, in the simpler function that we were looking at earlier, we basically only did one simplifying step before we took our derivative. But here we have a lot more going on. It's a more complicated problem. And so all those layers have to be kind of unraveled before we go forward. But now, again, everything else from this point on follows the same steps we did before. We take the derivative implicitly. So we get 1 over y prime. And then we take the derivative of the x side, just again, normally. That'll give us 2/3 x. The 1/3 derivative is 0 plus 5/3 log of tangent is going to be 1 over tan x times secant squared x minus 7/3, and then 1 over x to the 4th minus 6x plus 9 times the derivative, which is 4x cubed minus 6. And then really all you can do from this point is just a little bit of simplifying. You could do something with these tangents and secants. I'm just going to combine them into a single fraction for this purpose, because that's not the simplifying trig functions is not the point of this. But our next step then would be to then multiply by y to get our y prime by itself. And so 2/3 x plus 5 secant squared x over 3 tan x minus 7 4x cubed minus 6 divided by 3 times x to the 4th minus 6x plus 9. And then we replace the y with the original function, y prime is equal to our crazy original function times everything that we got from taking the derivative implicitly. And so we end up with this expression. There we go. We end up with this expression. So again, the original function appears in the derivative, but then also an expression that is derived from our logarithmic differentiation process. Now, as messy and complicated as this was, remember that the alternative to doing this is to, again, just to be clear, to do a chain rule. So you take the derivative of the 1/3 power, and then you do the inside, and you have to do, again, a product rule embedded inside of a quotient rule. And both the quotient rule and the product rule involve further chain rules in every component. And so, again, the strategy here is simply to make our lives a little bit easier. Because notice I didn't even use any product rules at all. I did use some chain rules because the expressions inside my logs were more complicated, but I didn't have to use product rules or quotient rules for that matter.